We want to be free to ride our machines without being hassled by the man.
Alright, back again, got this set up. So one thing as I didn't mention is I did not replace these two bipolar caps. They're 16 volt, they say they're 50 volts AC. I didn't replace them, they measured okay. And what they're used for is to dump they're attached to the output, the audio output, and they sense for DC offset, so it'll open up the relay if there's too much offset, if there's some failure. And they do that by dumping the audio AC to ground and through a resistor, of course. And if there's some DC offset, there's a time constant between the resistor and this, and then it'll shut off the relay. So what I have here is a supply. I don't know if we can see this. The positive lead is going to the positive lead of the meter, and then the negative lead of the meter goes to the cap. Negative lead goes up to the cap, and then the ground on the cap goes back to ground. So I have 2 meters. So I'm going to set this for microamps and just put this on DC. Put that on DC. Okay, and I gotta plug this supply in. Okay, so there we go. 1.25 volts, which is the minimum volts this supply will put out. And we have, there it goes, that's microamps. So 60 microamps, 50, etc. If I turn this up just a little bit, 1.2, what I usually do, I don't watch the voltage, I watch this, and I watch it as I turn the voltage up. I can see both at the same time, the camera doesn't. Here we go. So that's 1.5 milliamps going down, going down, going down, and now 1.3 volts. So what I do is I just keep cranking this up a little bit at a time. I don't have a series resistor, I'm just watching the current. Make sure I don't turn it up too much. A couple milliamps at most. Spikes. Now we're at almost 1.5 volts. And you just keep doing this. You know, you watch this meter and it jumps up, goes back down. It jumps up, goes back down. So, yeah. You know, if the weather is nice where you are, you can go outside and watch the grass grow. And if it's not so nice, you could paint something and watch it dry. It's about as much fun as doing this, isn't it? So I'm going to cut this off and just keep going. And this is my lower supply. It puts out 17 volts. Then I switch over to my higher voltage supply. Will go up to 90 volts. This is just, you know, home built adjustable supply with a regular Allen 317 regulator. The pot. All right, so I'm going to keep going with this. Just keep feeding a couple, the regulator has current limiting and everything, but now we're up to almost 2 volts, getting up there. Yeah, 2 volts out of 100. Yeah, we're getting up there. There's 2 volts, and they're just dropping off again. So you just keep watching. If the cap was really bad, this would be really high, because all the dendrites, you can get rid of all the dendrites, the growth inside the cap. It causes it to short out, and then you have amazing inrush current, and the cap blows out. Kaboom. So this is reforming a cap and killing all the dendrites. Those nasty dendrites. I think it was a dendrite killed my sister. All right. And getting up to 2.2 volts. All right, that's enough of that. We'll just keep going here. So this is a higher voltage supply. It goes up to about 90 volts. Because this one was working so much better, this capacitor was working so much better than the previous one, I decided I'll show you a different way of doing this, which is simply, you can't tell from all this, gobbledygook wiring in here, but I just grabbed a 27K resistor and put it in series, and I connected this up to the 93 volts before the regulator. So I'm putting 93 volts through a 27K resistor, and this is the current. You can see it's slowly dropping. It's 230 whatever, and that's the voltage across the resistor. Almost 7 volts. It's dropping as well. So by putting a series resistor in there, you limit the current. You want to limit it to, certainly less than 10 milliamps. Probably even less, maybe like 3 milliamps. So you can just hook it up to a... My meter's been on long enough. It wants to be turned off. If you have an adjustable supply, you can go up in chunks like 10 volts, 20 volts, 30 volts, 40 volts. Use a series resistor. Or if you have a bench supply that's adjustable, you can, which is what this mimics, do the same thing, or set it for whatever the value of the capacitor is, like 100 volts. So you need 100 volts, or pretty close to it. This is 93 volts. And a series resistor to limit the current. You can do it that way. It's better to do it in chunks so you don't get these big inrush current spikes that can damage the capacitor. That's why I did the lower voltage first. I didn't use a resistor, but I was going up, a milliamp, maybe 2 milliamps. I could see it on the meter. What I was doing is just, starting at about 1.2, 1.5 volts. I could go up very slowly and watch the microamps, which is not a problem. The previous capacitor showed it was lower than 75 microamps. I think it was down to like 40, 50 microamps when I was done with it. And this is certainly below a milliamp. It's less than 200 microamps right now and still falling. So it's a good cap. I probably didn't even need to do this really on this cap, but since the other one did need it and showed improvement, I decided to just go ahead and do this. because this thing has been turned off for decades. It hasn't been turned on for decades. So I just want to make sure these big caps are treated properly, so I don't have to replace them at, you know, $40 a pop, $30 a pop, $50, you know, whatever they run. You won't find these caps are obsolete. So the closest thing to it is probably 10,000 to 100. I think it's Vishay probably makes them. I think TDK still makes one of them. Oh, I think I have it listed actually. Kemet. Yeah, Kemet will still make different values. 10,000 microfarad, 13,000, 15,000. So, you know, if you had to replace these, anything in that general range, these particular ones are, the tolerance is plus 75%, minus 10%. So this one measures 10,000, which is within 2%. The lower one measures 9,200 or something like that. So that's about 8% low. So it's, you know, getting close to auto tolerance, but it's not. It could be, you know, 75%. 50% of 10,000 would be 15,000. So anything in that range, you're not going to find that. I think these are actually specially made for the. It has a company part number on there. It has a Altec part number on there. So those 9,800 is kind of a strange value. I don't know why they didn't just go with 10,000 microfarads, but I guess they had to be special. So you can see this thing's now getting down to 150 microamps. I just let it go. The voltage across the resistor was, when I started, it was over 30 volts. Now it's down to 4. Oops, sorry. There you go. 4 volts. So get that done. Get this done. I think I'll be ready to put it back together, which will probably be a little bit of a chore in itself. And I don't know if you have any, you know, you can put all your flames and arrows down below. Just write them in. I may not answer, but you can write all you want. And I think we'll move on to the schematic at this point. I'll go over that a little bit. Bye-bye. All right, you can see the schematic here. This is the power section, the driver. I think it's called the driver. Oh, that's great. Never get rid of that. All right, there's what I'm looking for. Heatsink power output. Board 1, board 2. All aboard. So they have 3, I guess you call them pre-drivers in parallel. And then they have the outputs. They have 4 output transistors per side. There's a current sense on the positive side that goes back to the driver board. You know, current voltage, whatever. Same thing here, goes back to driver. And they also have this one. And this is the center point. Here you see, oh, you can't see it. So you have the Zobel network, 6 ohm, 0.1, and output inductor, snub the high frequency, and, you know, where'd they go? These kickback diodes, because you're driving an inductive load. Speakers and inductive load, little kickback, anti-ring, you know, kind of thing, like on a solenoid relay. You see your reverse diodes. And so that's pretty straightforward for the power section. These are all on the same heatsink. Yeah, these are all on the back heatsink. Lots of transistors back there. Oh, look, a thermal cutout, 210 Fahrenheit. What is 210 Fahrenheit? It's 100C. I'll call it 99C. Close enough. Oh, 210. 212 would be 100, sure. So that's the power transistor section. And it all, for the most part, goes back to the driver boards, to the output pins on this side. This is a schematic is difficult to read. I have all these tie points, all these wires. Maybe you saw them in there. You know, to follow this through leads you on a nice little chase. So this is a driver board. The other thing they have to compensate for is when they put it into bridge tied load, BTL mode, then they have to set it up for mono, right? Well, it'll do dual mono. It will perform as a stereo 100% and BTL, but they have to bring the other side in, cut out one volume control and the other have a master volume control, so to speak. But here's the 5 microfarad 25 volt. Yeah. Here is the input cap. I made that a 10 microfarad bipolar. Here's the feedback. This is the this 40.2 and this 511 are 1%. And here's the 20. This is the N750 capacitor. Here's 50. I made this 100 at 25. I believe. Yeah, I made this 100 at 25. Open up the bottom end just a little bit. No big deal. Notice it has the diode to protect this cap. So if there's a catastrophic fault and you get, let's say your output transistor on the positive side blows and you get 80 volts power supply coming back, you might think this is a divider, but there's a capacitor here. So this is going to see the full 80 volts on a 16 volt. Well, with this diode here, it's going to create a path to ground. Believe it or not, this is ground. So you create a divider. And so it's going to be about 1 volt there. If this is 80 volts and this, I think this is like 80 or something like that. So it's close. This will only be a volt right here. So you'll save your capacitor. That's why I put the reverse diode on here. So if the negative side blows and you get minus 80 volts, you still have a path. Especially a reverse path on the capacitor, you save the capacitor. I don't know, saving a capacitor on very expensive transistors that are probably blown. I don't know what it gets you, but I guess it gets you something. So that's why I did it. And this is a cap I didn't change. Just left that the same. This may look like, you know, initially when I just looked at this, oh, they're bypassing this point. But at some point I started thinking about it and thought, well, what about on power up or power down? What's happening? Well, this is minus 80 here, or 45 if you're in lower power. But when you turn this on, this is a short. What happens? That means it's going to push this. It's not going to turn this transistor. This transistor is going to be turned off until this cap charges up. And this thing can start doing it. Then this thing, 3 volts, right? It sets the current through here. and the bias adjust. So I think this is acting actually as a type of soft start. It's not just filtering this point. This is ground. This is kind of drawn a little funny. But, so you're setting up 3 volts base emitter, 3 volts, well, 2.3 volts will be here. And divided by 270, so that's the current through here. It has a bias adjust. Yeah. And it has one of the standard null outputs that feeds back here. So a lot of times they get fed back right into this transistor, but they fed it back into the bottom end of this side. Yeah, and a lot of protection circuitry, current fold back stuff, and this is where those sense points from the power transistors come back in. This is the audio output here. Center, the common, audio common, not ground, just its common output point. So, what are the, it looks busy, very busy, but it's not far off from probably other amps you've looked at, schematics, amp schematics. More of the whole thing here. Differential pair on the front end, setting up for, whatever current, a couple milliamps probably, whatever. And protection circuitry, pre-drive drivers. So, what are the secrets of this amplifier? They lie here on the control board. Yes, they do. And I'll show you something. I'll get right in where there it is. So, here's where the AC comes in. It gets full wave rectified. Notice there is no filter cap. So you're getting 60 hertz going negative. These are the light bulbs for the display, for the meter display. 30 volt Zener on this transistor is acting one of those not very good regulators typically, and there's no capacitance here either on the emitter. And these are high side, they're not to ground, they're high side. So here's the 1K on the base, and I stuck a 5K pot, actually I put it down here, in series, so I can adjust this base, and we'll see how that works out. But, these things are operating off a negative voltage with this transistor in here, high-sided. So if you put LEDs in here, if you were just going to put LEDs with a resistor, you had to make sure you get the right polarity on your LEDs, because this point here is negative, more negative than this point, which goes to ground, ultimately. That same transformer AC comes in here, gets halfway rectified, filtered, and that creates the voltage for the relay, which comes around. I sort of drew it in here once upon a long time ago. The thing that throws you off is this 100 ohm resistor is going to drop some voltage. So where does that go? It goes in here. Now this circuit, let me jump over for a minute. Notice I have 45 volts here. comes in, there's a resistor here, and it goes to this diode. It'd be really nice if they had drawn this diode over here, because certainly when I'm looking at it, I tend to think, oh, there's 45 volts here. No, there's 12 volts. 12 volts in it. If they put the 12 volt zener right there, then it would be nice. Is that coming across? Oh, maybe not. Sorry about that. Let's get up here a little higher. So here, 45 volts comes in. The resistor, if the zener diode was here, it would be really obvious that all this was 12 volts. This whole circuit is running off 12 volts. Okay, but what I want to show you is that 12 volts comes down to the base of that Darlington. So this is the offset circuit. So what happens is the positive relay positive voltage goes to the positive side of the relay. Sometimes it doesn't matter, positive, negative, but it comes back in here. And what's happening here? That this is going to have a drop of a couple volts across here. So this is probably more like 26 volts, not 24. It's a 24 volt relay. I suspect one of the things I want to measure is it's probably 26 volts. And it comes back here, and what happens is it comes through the here. It can't. This thing is off. This has 12 volts on the base, so as long as everything's good, this is wants to turn on, but this is off. So the voltage from the relay comes in here, 56. It goes through this 12 volt zener, and it charges, and you have this 200 microfarad cap sitting right there. So this is a time constant. And it charges up to whenever this breaks over 12 volts, whatever. Fires the gate. This thing turns on. Relay conducts. Everything's honky-dory. All right? That's how that works. But how do you turn off? You have to interrupt. In order to turn this off, this SCR off, you have to open up the anode and cathode current. Also what happens is, notice there's this diode here, so 47 ohm. So once this does turn on, this cap discharges very quickly through this path, through the 47 ohm diodes. The reason I stuck the 1 meg on here is because this is going to have a 2 volt drop, or thereabouts, you know, whatever it is. Yeah, 1.4 and 7, 2 volts, 0.7. So this is only going to discharge to about 2 volts. So you're not going to get your full time constant. I stick a 1 mega on here so that when it's off, this will discharge through the cap. This is ground, so it'll discharge through the cap and bring the cap down to 0. The 1 meg affects the timing a little bit, but it shortens the timing just a tad. But you know, even if it's a tenth of a second, who cares? This is probably in the 4 to 5. I think this is more like 5 seconds. And this wasn't 200; it was 220, and I put a 220, reinstalled a 220, new one. So what happens is this line right here is sensing the audio. A lot of switching here. A lot of the switching has to do with the dual mono bridge tied load stuff. This gets rid of the pot. This becomes the master pot. But it's monitoring the audio, right? So normally you don't have any offset, and you've got your music playing, boom, 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 and it's just this capacitor, that 16 microfarad 50 volt that was sitting there at the top of the control board. It's just dumping that to ground. So nothing's happening here. If you have a failure and you get some DC offset, there's going to be a time constant. This is going to go positive, so it's going to go through here. It's going to turn this transistor on. Transistor is going to turn on, pull this to ground. This turns off, which interrupts this, which turns off the relay. If it's a negative voltage, this blocks the negative voltage, and it's going to pull it, counteract it directly. And at some point you get below the voltage on this guy, and so it'll turn off with a negative. So this is just the other channel. It does the same thing. Positive DC voltage comes in, turns on the transistor, turns this circuit off, turns the relay off. Negative voltage comes in, and this limits. So for negative voltages, this is going to limit the points. The max it can go is minus 0.7 volts. So you don't burn out your transistor with negative voltage. This up here, so this is a 10 microfarad I put. What was it? Oh yeah, yeah. This is a 10 microfarad I used the tantalum on. The other one was on the driver board. I think it's up here. So this one, I put a 10 microfarad 35 volt tantalum in here. And so which way? All right. So this, what this circuit is a transistorized, basically it's an exclusive OR circuit. So either this one's turned on or this one's turned on. These control the triacs that will change from 80 volt, 100% to 40%, 80 volt, 45 volt, whatever. So what happens here? Well, where to start? 12 volts up here, 45 volts is the inner diode, should be right there, 12 volts. Notice this goes over to the switch. So if you put it in 40% mode, either mono or dual, which is these two, it's going to come back here, it's going to turn this off. It's going to ground this, turns this off, which means this is going to turn on, so you're in 40% mode. And it obviates the circuit, won't do anything. This is a temperature circuit, so because you're grounding this out directly, this isn't going to do anything. What is this for? It's for it's a temperature protection. What happens is there's this, oh, you can't see that. Pointing over there. All right, let's move this over. Well, I'll move this over. Okay. So what I have drawn in here once upon a time ago is this this resistor, thermal resistor. And it's out there on the heat sink somewhere. And so what happens is you get the 45 volts comes in here, and this isn't going to be turned on. So this is high. This is a high impedance. This is a negative temperature coefficient. So as it heats up, the resistance is going to drop. Less and less resistance. When that happens, see, it comes in here off this circuit, and it comes back around to this gate. When you get low enough voltage, high enough voltage, this drops, this becomes high enough, it's going to trip this and ground it. Same thing happens, right? Whether you ground it here, you ground it here, it's going to switch this over to 40%. So you're on 100% mode, dual or mono, this thing gets hot and trips, and boom, it goes over to 40% mode. The funny thing is, I don't think you'll know it. There's no LEDs or lights or anything to tell you anything's happening here. So if you got this thing cranked up, you're on 100% mode, 80 volts, you got it cranked up, but this thing drops to 40% mode, I would think, unless it's changing I don't think it is. I was going to say unless it's changing the gain of the amp, which I don't think it does. It's probably going to go into, you're going to a lot of distortion. It's going to clip. It's going to start clipping and sound like crap. So you're not going to know what's going on. You maybe turn it off, turn it back on. But it sits for a while at 40%, cools down. If you you probably maybe go over and turn the volume down, and eventually this thing will come back on, because when this goes to ground, comes down here, turns this transistor on. This transistor passes this 12 volts into this circuit. This is unijunction transistor. As you get the voltage here, the resistance between base 1 and base 2, I don't like the nomenclature on these guys, but whatever, reduces. So what you've made is kind of this relaxation on this 1 meg, 10 microfarad tantalum that I put in here. Creates an oscillator. What's happening? Well, it's going to oscillate, and it's going to put pulses across this cap. When that happens, it's going to try and open this up and clear that. But if the gate's still there, if this thing is hot and it's still putting a gate voltage on there, it's just going to stay turned on. You'll stay in 40% mode. So this thing's going to be on constantly trying to open this up. At some point, when it cools down, this resistance goes up and the gate voltage goes away. It's going to put its pulse across here and turn this thing back on. It's going to switch it back over from 40% to 100%. So, I don't, I never had a use for a unijunction transistor, and I don't think I would have thought of a use for one. These are still available. This 2N2646, I think they're still out there, still manufactured. But and this is looks like a stabilizer, so it has a certain voltage drop. It's setting up the knee on this resistor. So this has to happen kind of fast. It has to kind of hit a certain temperature and pop over, turn that on, and it'll switch to 40%. So if you have one of these by some chance, and you got it cranked up, maybe you don't have the fans on it, like me. I don't run it with fans, or I run it without fans. If it starts crunching, get all that, it sounds like a fuzz box. You need to just turn down the volume. Turn down the volume so it's not so loud, and let this cool down, and then switch. Put it in 40. Just put it in 40% mode yourself. Just flick the switch over, put it in 40% mode, which it's in anyways. But it's kind of a weird, what, I don't know, I spent money on this because, yeah, these are just up here. So that's what all that's for. It's just a switch between 100% and 40% mode, and a little bit of safety, thermal safety in here. And this is just a meter. They bridge rectify the audio and send it to the VU meters. And the attenuator. So if you're playing loudly, set it up here. Playing lowly, you set it up here. Playing loudly, you set it more division. And that's it. That's kind of, this is the thing I wanted to get into. I want to check this out a little bit more. Maybe I can get in here and put a scope on here. The rest of it I understand fairly well. Yeah. Some version of these are all available. Nothing here that can't be bought. You can be had. Notice and you see all this wiring. So you have to follow from one page to the next page to the other page, trying to figure out where everything's going. They have these triacs. Yeah, these are triacs. You have triacs 4 and 2. Where are they at? Oh, it's probably these. These are the triacs for the 40%, 100%. So you have 2 bridge rectifiers, 40%, 100% power, and the on-off triacs, dual. So that's why these on-off switch is a double pole, single throw, double throw, whatever. That's a double pole switch because you're keeping these two separate, turning them on and off separately. So there's this kind of block wiring diagram here. As a matter of fact, I got it here. Right there. You can see here's the power switch, A and B, double pole, single throw. These people are selling like single pole, single throws. But I was looking for capacity. I was looking on eBay and I saw people were selling capacitor kits and switches, and they'll even sell knobs. Altec knob, and it's not an Altec knob. It's too big. They're bigger than they're supposed to be. So don't fall for that stuff. Just go to Mauser. Just take an inventory of what you want to change. Go to Mauser, DigiKey, whoever your favorite person is, and buy them through there. Buy your capacitors and whatnot. I don't know. If you break a knob, lose a knob, go out and buy some different ones. That'd look nice. What was I gonna? Oh, I know what I was going. And it has a bill of material in here for all the different boards, chassis. There's a block diagram, and what I was gonna say is that where's it at? It has primary control, on off, and low voltage, high voltage, DC detector, latch breaker. But what am I looking for? Here's that thermal. Goes back to the reset latch. I was looking for, oh, I know what it was. Somewhere in here. Well, I cannot see it. I'm blind. Somewhere in here, if you see it, I don't see it. You probably don't see it either. It said voltage regulator for the meter. There it is. There it is, right in the middle of everything. Rectifier, regulator, meter lamps. A3 CR19 Q7. So they call it a regulator. It is a regulator. I'd have to redraw it for you. They're used a lot of times. The regulation, as long as you don't have a very dynamic load, they work okay. But they usually also want some kind of capacitance on the emitter to keep that, to regulate. So I'm curious about how well this thing's really going to work. It does work. I don't trust it per se. I'm wondering, yeah. One might say it's a current source, but driver boards, so the whole shebang, control board, all the wiring points. Yeah, so this is a difficult schematic to follow. I've had it for this thing for a long time, and occasionally I've gone back over this thing, so I have some sense of where things are and what they do. Yeah, secret circuits, lighting regulator, relay, DC detect, and voltage switching, power board. So that's it for the, well, there's one more thing. Let's see how we do here. There it is. There's instructions in here about setting the bias, strappings for different voltages, AC voltages, how to hook things up if you want to. If you want to add amps, if you want to daisy chain amplifiers, you want to biamp, multi-amp, balanced input connector. This requires a transformer. I showed you those octal sockets. I don't even know if you can find these anymore. I wouldn't worry about it. I didn't use them. Yeah, somewhere in here. Fuse replacement. How to replace a fuse. Anyway, somewhere in there is the bias adjustments and whatnot. So that's it. Moving forward.
The